Let's quickly go over the solution to this problem. So we didn't discuss anything about the microscopic details of the problem or the forces involved. And so in order to relate what happens here to what happens here, we're going to need to use conservation laws only. And so we know that energy momentum, the total energy momentum before and after has to be conserved. And so we'll just write down the two kinds of energy momentum here and the one kind of energy momentum there and equate them. So here we have this photon momentum. Because mass is 0, the energy is just Pc. And here we have just a rest mass, and so it has no velocity, it just has this, and gamma is 1. There's a 0, 3 vector. And then over here we have a non-zero momentum, and we have a changed mass, where this P is the momentum that we don't know, and this ME. So we've got two unknowns, or indeed 4, because we've got 3 in that vector and 1 in that mass. Fortunately, we have 4 equations, which is that this plus this equals this. And so we have, and we equate them term by term. Now clearly the momenta are very easy to equate. We already have that the momentum of this thing must be the momentum of the original photon, because there was no other momentum in the problem. And so now we equate the energy terms, and we have that where we've replaced P with P lambda from here, and we simply rearrange this to solve for the new mass. And there are our answers, solved. Now let's examine a situation from electromagnetism. What I have here is an electron, and here is another identical electron. And because they're both electrons and they're both negatively charged, they're going to experience a repulsive force, equal and opposite of size, where they're separated by a distance r. For an electromagnetism problem, that's so simple because everything's still. However, it's only still in one particular frame. In fact, we could move into a frame where both of these things were moving. They would have to be moving the same way, so let's give them both a velocity v, the same velocity v. Now when you have a moving electric charge, you still have the electric force repelling them, but you also generate a magnetic field. So this electron here is going to be generating a magnetic field in circles around its direction of motion, and indeed that would normally be using the right-hand rule because it's negatively charged, it will be going the other way. And so when we come and look at this electron, the magnetic field due to this electron will be going into the screen, and correspondingly the magnetic field for the other electron will be coming out of the screen. So the size of that magnetic field is going to be same r, and then that magnetic field is going to induce a magnetic force. And the size of that magnetic force is going to be QV cross B, and so they're all at right angles, so I'm going to get the electron charge, the velocity, and this magnetic field. So there's going to be some velocity at which this magnetic force actually is precisely equal and opposite to the electric force. Let's work out what that is. So electronic charges cross out, the 4 pi r squareds cross out, and we're left with, and that is a fairly familiar velocity. That velocity is the speed of light. In other words, if we move into a moving frame, eventually these electrons appear to stop repelling each other. From a special relativity point of view, you'd expect that as you move into a moving frame, time should slow down. And indeed, as you go towards the speed of light, you'd expect time to indeed stop. And that's exactly what this electromagnetic theory is giving to us for free. So we don't have to apply Lorentz transforms to time and space. The magnetic fields are precisely doing that for us. So in fact, electromagnetism is giving us all the special relativistic effects for free. But what we'd really like to do is see that that theory is in some kind of vector or tensor form that is explicitly invariant between reference frames. Now in order to do that, we're actually going to have to expand our notion of 4 vectors all the way up to tensors.